Good afternoon, everyone. My name is Dorota Koziel-Wierzbowska. I'm from Jagiellonian University in Krakow, and I am a chair of the EAS 2023 hosting committee. Together with Jarle Brinchmann, I will co-chair the Tuesday plenary session. And the plan for today is that we will have 3 plenary talks and Lodewijk Woltjer Lecture. So we will start with the talk of Professor Reinhard Genzel, director of the Max Planck Institute of Extraterrestrial Physics in Garching, and professor of the Graduate School at the University of California. He is the winner of numerous awards, including EAS Tycho Brahe Prize in 2012, and the Nobel Prize in 2020 for the discovery of a supermassive compact object at the center of our galaxy. So his main interest is focused on the formation and evolution of galaxies, massive black holes, and the star formation. So today he will talk about galaxies and the high-resolution observations of supermassive black holes. Please, Professor.
Well, dear colleagues, the topic of galaxies and black holes, of course, is vast. I cannot speak about all of this, but I would like to report to you about the progress we've made as a community in proving that the predictions of Albert Einstein and others 170 years ago indeed are realized in the universe. Now, of course, this kind of work, this experimental work, really has been going on for some time. In my own period of work, for more than 40 years, gravitational wave discoveries over the same period of time, which tells you a little bit about the instrumental difficulties we are encountering, and I'll try to briefly say a few things about it. Now, of course, why are we interested in black holes? As physicists, because there are aspects about Einstein's theory which I would say are likely not going to be right. And that's the quantum part of it, that's the singularity, the exact shape of the event horizon, information paradox, and so forth. As astronomers, because we are wondering, of course, what the role might be if these objects called black holes really are there. The stellar black holes as remnants of massive stars, and the massive black holes as what? What is their role? Now, to do this, you need a resolution. Although black holes, especially massive black holes, are big objects, a billion solar mass black hole has about an event horizon size of the Earth orbit, but they're still very compact, especially at large distances. So you need big telescopes, high sensitivity, and particularly the techniques of interferometry. So I'll, in my talk, report about the results of 2 paths forward. One, to use optical infrared interferometry with the 4 8-meter class telescopes of ESO with an instrument called gravity, which we have developed over the last 15 years. And then I will also, of course, mention the equivalent kind of work with the Event Horizon Telescope of combining radio telescopes across the globe for millimeter interferometry. Of course, these techniques, as I said, were long in coming. Case of optical interferometry, already in 1920, that was tried and achieved results on bright stars, but it took really a very long time to break through a number of technology burdens until we can do now really very faint source interferometry. In the case of interferometry in the radio, of course, that developed smoothly, more smoothly after the Second World War than the recording of waves in tapes and then going slowly to ever shorter wavelength. Now, this kind of work cannot be done by single individuals. So really these are teams. As you know, in the case of the gravitational wave discoveries, we're talking about several thousand workers. In the case of the Event Horizon group, that's several hundred. We are the smallest of these teams of about 90 people in 7 institutions, including ESO. And I'm very proud to say that it's really that combined work in a team over many years which has made possible the work I'm telling you about. Now, of course, the issue of applications in astronomy really started in the 1960s with the discovery of the quasars by radio astronomers. The fact that there are very, very bright radio sources which then on optical plates have a substantial redshift, such that if you interpret that redshift as a measure of distance, these objects must have luminosities of 1,000 to 100,000 times the entire luminosity of Milky Ways, yet the radiation emerges within a fraction of a light year. That was the puzzle and led, as you probably know, to a period of deep thinking by a number of the best theorists in the world to try to understand how you could generate energy. Certainly not in the way you generate energy in stars, but the work of Lynden-Bell, Rees, Sanyaev, Blandford, and others really made it clear that at least theoretically, if you let material spiral in or fall onto a massive black hole, and before the material disappears within the event horizon, you can convert between 7% for a zero spin and 40% for a maximum Kerr black hole into radiation. So that's 1,000 times more efficient than fusion. So that's been our paradigm. To prove the paradigm, you should use gravitation. That's pretty obvious because if there is an object which doesn't radiate but has a lot of mass, you should see in the environment, in this accretion disk, for instance, very high motions of the gas. But that, at the time these theoretical predictions were made, was not possible. It is possible now, I should say, with gravity. We are measuring the motions of gas in the broadline region at redshift 2.5, but at that time that was not possible. So the paper by Lynden-Bell and Rees in 1971 was a key step forward, who said, well, maybe quasars, which are very rare, are rare because only in some rare circumstances does a galaxy accrete so much material that so much energy is released as in a quasar state. But if that is the case, then maybe other galaxies, including our own, might also have a black hole, although not active. So that was the proposal, followed by a fairly detailed account of what the astronomy observation community should do now in the galaxy as the nearest object by a factor of several 10,000 to verify that there is a massive object. Basically, look at the gas clouds in the galactic center and see whether they move very fast. They didn't think yet at that time about the stars, but certainly the gas was at the center of the idea. So in the 1970s, it really became possible to look at the center of our galaxy in various ways on a scale of a few light years. If you look at the central picture there you see the distribution of the gas, ionized gas in pink colors from the radio observations, and then in green here, the neutral gas. And in the center of all of this, a compact radio source called Sagittarius A star, which radio interferometry in the early years already, in the mid-70s, identified to be unresolved. Now, over time, the interferometric techniques in radio astronomy got ever better, such that we knew within the next 10, 20 years that this object really was a source where when you go to a very short wavelength, which is less than a milliarc second and even less than 100 microarc second in size. So that sounds like X marks the spot. That could be the center of the Milky Way, and then the interpretation of this gas cloud could be swirls of gas tied to and tidally disrupted orbiting the black hole. Now, you cannot, however, measure these motions in the optical because of the extinction is so high in front of the galactic center. So Charles Townes was the first one with his students, and I was then one of his postdocs, to use infrared spectroscopy to measure the Doppler motions of the ionized and neutral gas. And indeed, these motions were so large that in the central region here, around Sagittarius star, both the ionized and the neutral gas pointed towards a central mass concentration. A central mass concentration on a scale of, say, 10 arc seconds, that was what was then possible, and of a few million solar masses. So in 1985, we wrote proudly a Nature article saying there is a black hole in the galactic center, but nobody believed us. Why not? Well, because, first of all, gas is not the best tracer. There are other forces which can push gas around, especially ionized gas. There are magnetic fields in the region which could distort the motions. So you should have a better tracer, stars. And the second one is, when we were measuring here on a scale of a few arc seconds to 10 arc seconds, you are a million times away from the event horizon of a few million solar mass black hole. There could be a lot of other stuff in there, and many people were highly skeptical that this could be the case. So the step forward from here, when we started in the late 70s, early 80s, to where we are now, is basically stepwise improving the sensitivity, the resolution, and further and again over several orders of magnitude, and then and again and again and again. And so that has brought us forward to now the scale of the event horizon, which in the galactic center for a 4 million solar mass black hole is 10 microarc seconds in radius, or 0.08 AU. Okay, so that's a very small scale. As you see, the trick is that we turned out to be lucky, that there are stars in there which should not be there, theoretically, which have peri-radii of only about 30 to 120 AU. So that's about 1,000 or less Schwarzschild radii, so deep into the relativistic zone of the region. So in the current epoch, of course, we are helped enormously by the VLT. Individually, with the 8-meter telescopes per se in the first 20 years, but over the last years, by combining the 4 VLTs to an interferometer with a maximum baseline of 200 meters. That gives us about 3 milliarc second full-width half-max resolution, and the astrometry we can push to about 30 microarc seconds, so 3 Schwarzschild radii. So that's a tremendous step forward. And the techniques which gravity presents are about a factor of several thousand times more sensitive than optical and infrared interferometry still 10 years ago. So there has been enormous progress which allow us to see stars of about 20th magnitude. So when we started with seeing limited infrared observations in the center near Sagittarius star, which is here at the center, we barely could see some bright stars, which are stars of the type that Selma talked about, very bright O and Wolf-Rayet stars. But then with the technique of adaptive optics on the 8-meter telescopes, both our group and the group of Andrea Guess using the Keck telescopes were able to improve the resolution, as you see, by a large factor, about a factor of 30 or so, and so you can see many stars in the vicinity of Sagittarius star. Now with interferometry, you can look now at this central dot here, which is Sagittarius star, and look at it even with another factor of 30 higher resolution, such that, in fact, see in 21, observations at different times in different colors show you how individual stars zip by the galactic center with about 2 or 3% the speed of light. So that is an enormous measuring capability, of course, which we have available. The progress is still going on very rapidly as we improve the capabilities of gravity to gravity plus. This is an image we have taken this last year, again, of the central region, and you can see how rich the environment is. The reason we are so excited about this is that the closer the stars, of course, they get to Sagittarius star in their motion, the more likely it is that we pick up effects due to the spin or even higher order effects of general relativity. Okay, the first big result we can certainly report, both groups can report, is that this work, both in terms of the astrometry here of one star, S2, which gets to a distance at Perry of about 17 light hours, so that's 120 AU, to Sagittarius star, with a velocity of about 2.7% the speed of light, and an orbital period of 16 years. So this is a wonderful, laboratory animal, because it comes around, and you can only, improve in the meantime your interpretation. The interferometry is so precise that at Perry here in 2018, we could see the motions not anymore from month to month or so, but from day to day. So here was Perry on May 19th, 2018. The star is already up here again, close to Apo. The other strength we have is we have a number of such orbits now, such that we can co-fit various nuisance parameters like the 0 points in space and also velocity out. And that's a key element for the, as you will see, effects like the precessions, in particular the Schwarzschild precession. So the number we are getting is a number on the mass and also on the distance, which is unprecedented in accuracy, to about 0.2% in statistical numbers. So the two errors you see quoted as statistical and systematic error bar. And the UCLA group lately has revised their number also, such that the two measurements are, now in very, very good agreement. So these are extremely precise numbers for astronomical standards. Okay, now as to testing general relativity. The first effect you would expect of the order of V over c squared, so on the order of 3 × 10⁻⁴, is when the star passes by the black hole and sends a line emission towards us, that this line emission is redshifted. So that's the gravitational redshift, very well known. So if you, in the lower curve here, subtract the orbital motion, which of course is contained in here due to Newton, such that as a function of time, you only look at the residual in velocity space, such that Newton is always 0, then the prediction by GR is that red curve. And the observations are the cyan data points. So if you introduce a fit parameter where the fit parameter FGR is 0 for Newton and 1 for GR, well, you see we are there's a 25 sigma detection of general relativity. Both groups have now made that test and have verified that the effect is there. The next slightly more difficult effect is the Schwarzschild precession. Remember the precession of the orbit Mercury around the sun, which was one of the early triumphs of Einstein's work. So here, recall that if you have a central mass and then a second bound mass on an orbit, to speak in Newtonian terms, say an elliptical orbit, then in Newton you would always expect that orbit to stay in the same shape in space unless there's a perturber. Not so in general relativity. In general relativity, the orbit precesses forward, in the case of the star S2, by 12 arc minutes per 16 years. that is equivalent to half a milliarc second shift of the orbit. So let me plot that in the same way in residuals as here, but now, of course, we are plotting x and y in residuals. So the Newton equivalent point is just a point, right? So there's no change relative to Newton. That's subtracted. Now, the prediction by Einstein's theory are these little loops, which of course are the precessions relative to the Newton orbit. So that's what you should be seeing, where the parries, the two parries which we have seen so far are here and here, the two appos are here and here. And so if you now plot the data with the interferometry, you can clearly see how beautifully we see the Schwarzschild precession at a level around 13 sigma. This is a tricky measurement, more tricky than the gravitational redshift, because of the nuisance parameters I mentioned. They have to be controlled, and with the adaptive optics data only, that was very, very difficult. With interferometry, that has completely changed. Now, these stellar motions are on a scale of 1,000 Schwarzschild radii, so we would like to go closer, of course, and measure there, and I'll report about that next. Now, the fact that the Schwarzschild precession is so extremely well followed has immediately a second effect. Namely, imagine that there is another mass, be it an intermediate mass black hole, or a whole halo of stellar black holes, or other masses in or near the orbit of S2. Well, then they, of course, are a perturbation and would introduce a Newtonian retrograde motion. That's very clear. You can compute that, and you can reversely go ahead and take the data and ask the questions, given the data, how much mass could there be at what distance away from the black hole other than the black hole? And the answer which emerges here is this this Monte Carlo analysis, this very ratty contours here, but all within about 2,000 or 3,000 solar masses. So within the outer orbit of S2, there cannot be more than less than 0.1% of the mass in terms of another mass. This is astounding, because many people, to start with, would have expected perhaps the black hole to have an intermediate mass black hole around it, because there are various effects in the galactic center nuclear star cluster which point towards very fast development tiles, much faster than the two-body interactions. And so many people betted that there might be an intermediate black hole. That we can exclude. Another option of a large cluster, say 100 to 1,000 stellar black holes, also very likely due to just sinking of the stars, of the heavy stellar black holes toward the center, also can be excluded. Within the orbit of S2, there could be a few stellar black holes, but not more. And finally, many people also, of course, have proposed that there might be dark matter in the center. And I'll come back to this. This is, of course, an option which we should take very seriously. If there's a black hole, then dark matter would be accreted and stay around as a halo, and maybe it's very substantial. Okay, but now, how can we get still closer to the event horizon? And the first method is we're using the emission from Sagittarius star itself in the infrared. Here's a time series of flux recordings, not contiguous, in the galactic center, where you see that the emission from Sagittarius star in the K-band is continuously variable. It's a bit of a red power spectrum, sometimes flaring up by factors of 30 to 50 above the normal level. Now, in the normal level, there is a steady emission, of course, in the radio due to synchrotron emission on the scale of about 100 microarc seconds. But when a flare occurs, then there is an infrared contribution. In fact, in some very bright flares, you could see even an X-ray component appearing during that time. Typically, once every day to once every week can that be observed, and these flares last for a few hours typically. So the question was from the very beginning, maybe what you're seeing here is the energizing the acceleration of material to very high energies, which then produce infrared synchrotron emission. And indeed, that's our current interpretation. Then you would expect that these might be hotspots which could move. And indeed, we can measure the astrometry by now of a number of flares and co-add them, as well as the polarization and co-add that, and we see a very beautiful pattern of a clockwise motion of all these flares over the last 5 years. And we can measure the orbital period, typically an hour at around 9 RG, or 1.5 times the innermost stable orbit. We can determine even the location, which tells us that the motion is almost in the face on the sky, and we can measure a mass of 4.2 million solar masses, consistent with the mass which we know to 0.1.2%, but now at 9 RG. The last point I want to mention here is the radio emission. You can, of course, also use photons to measure mass, because photons are influenced by gravity as well. So if you imagine there's a light source, and you're looking at this from the left side, the black hole is in the center, then of course, those photons inside here, a characteristic radius of about 2 RG, will be drawn into the black hole and not arrive. So we will see, so to speak, a dimming of the emission. Outside, then there will be a bright ring. And our VLBI colleagues have indeed been able to see that. There it is. Published last year. And if you take the mass, which you measured from the stars, and the distance, which you measured from the stars, then we have a prediction that this ring should be 50 microarc seconds. And sure enough, that's what the radio astronomers have measured. So this is a, prima facie test of a hypothesis where you have a prior, very, very clearly, the mass, which you determine from this radio emission, is also 4 million solar masses. So then, in summary, historically we started out here in distance from the event horizon. And we worked our way inwards by measuring ever better the motions of stars. Both groups, UCLA and the VLT group, get the same results. That's very satisfactory. And then we can exclude that there's much mass out other than the black hole. That's what I discussed with you. So what about this dark matter? Could there be any dark matter? Well, these measurements which I just showed you from the motions of the hot gas and the event horizon shows that the mass is identical to within the arrows with the mass out there. You could, given the error bar, still have some amount of extended mass as a dark matter halo, but it is very, very little. So in the galactic center, we can now say, after 40 years, yes, this is, with high probability, a black hole. Does it have spin? We don't know yet. We need to measure better. We are fairly confident that we perhaps can do this. If not, then LISA in space in 15, 20 years might do the same with gravitational waves. We are in an extraordinary period of experimental work on black holes. Many say black holes are the atoms of the 21st century. I believe it is tremendously exciting. Thank you.
Thank you. Does it work? Yes. We have time for questions. Okay, there is one.
If you use the dark matter halo, which is consistent with the rotation curve in the outer part of the galaxy, do you have a prediction what you should do should see inside, close to the Sagittarius?
Yeah, you have a prediction, but that prediction that has already been discussed in the literature 10, 20 years ago is so uncertain because, of course, whether or not NFW profile, is the correct answer is not so clear. But anyhow, yes, there is a prediction, but it's soft enough that it doesn't tell us. And we have to really go in there.
So it's below what you see as a contamination of extended material, right?
But what we see there in terms of dark matter is essentially negligible. I mean, I would say it is below an NFW. Let's put it this way.
Okay, thank you.
Other questions?
I would like to ask you, what do you think about how we can really fast measure if the black hole is rotating or not? What observational technique should we use to measure?
Fast. You want fast. You want speed.
Well, in the near future. In the near future.
Yeah. Well, look, I mean, I think in principle, what you need is you need to go to higher order in these perturbation terms, okay? And so we are now we are working towards our P2. P2 is the lens steering position. The lens steering position would say that in addition to this prograde Schwarzschild precession, you also have a wobble of the star around the black hole spin. That's what we are after. This we cannot do on the star S2, which you've seen. Although there we measure the Schwarzschild precession so well, the lens steering precession, even for a maximum Kerr, would be about a factor of 80 times less. We cannot do that. So we need a star which is further in, because of course the strength of the P2 effects are much stronger. They go like 1 over R, right? So that's what we're trying to do. That's why we're pushing so hard on the sensitivity to perhaps see stars going still further. And the hope is, I could say, very high. Because over the last 2 years, we've improved the sensitivity of gravity by a factor of about 30, still more, and we are seeing still further stars further in. So that gives us great hope. The other method is the event horizon measurements more precisely, because then you could see the actual resonance of the photon orbit. What you're seeing now is sort of a smear. That's not good enough. But if you really have high resolution and high sensitivity, then you could do that. I would say they will try. The Earth has a finite radius. So one option is to go into space. That's too expensive, I'm afraid. The other one is go to higher frequency. They will try that, but that's not easy because at 0.8 millimeters, the Earth atmosphere does not transmit very well, and it will be very difficult to get enough telescopes at any time. Still, this ought to be tried.
The last question.
Thank you. So, great talk, as always. I was wondering about the origin of these, or how did these massive stars get that close to the black hole? Yeah, they could not have formed there. What is your opinion about that?
Yeah, well, that's the 300,000, not a million, but a $300,000 question in astrophysics, okay? Clearly, the normal two-body interactions won't do it. I mean, that we clearly know. We need a much faster action. Many people, again, use the intermediate mass black hole because then you can get very strong injection into the lost cone orbit. But since we don't have such an intermediate mass black hole, we need other things. And so we need a heavy, or many, many heavy objects to make this scattering. And people have proposed all kinds of ways. I, as you well know, believe that a far distant interaction with, say, a massive giant molecular cloud can inject enough stars into lost cone orbits through the so-called Hills mechanism. And indeed, these stars, which we see in there, all have very high eccentricities, which is a hallmark of the Hills scattering mechanism.
Thank you very much. Let's thank Professor again. And we move on.
Okay. Okay, so hello everybody. I'm Jarle Brinchmann from the Center of Astrophysics, University of Porto, but I'm here on behalf of the EAS Council. And it's my great pleasure on behalf of the EAS Council to present this year's Lodewijk Woltjer Lecture, which is Professor Isabelle Baraf from the University of Exeter, as well as University of Lyon. Which is our, the award is given for her fundamental contributions to the understanding of low-mass stars, brown dwarfs, and exoplanets. I'm sure quite a lot of you are familiar with the Baraf et al. Models. You probably used them, all of you. It's been, ever since the brown dwarfs really started founding in 1995, Professor Baraf has really led the understanding to understand these kind of low-mass systems, and it's a great pleasure to have you give the Lodewijk Woltjer Lecture, and please accept the diploma and award.
Thank you very much.
And we will now dive into the secrets of the interior parts of stars, and I'm sure we're all looking forward to hearing what you have to say. So please, the stage is all yours.
Thank you very much. So I guess, okay. So good afternoon. I think it's quite impressive first of all, to talk in this fantastic lecture theater and to talk after a Nobel Prize winner. So I'll try to do my best to attract your attention. And I'm very thankful to the European Astronomical Society for this award. I'm very proud, and it's a great honor. And it's a great pleasure as well to give this lecture. But I'm not going to talk about the reason why I got this award, which is brown dwarf exoplanets and low-mass stars, what I call substellar objects. No, what I would like to talk about is about stars and trying to, I would say, answer the question, how could we improve stellar evolution models? So, first of all, why should we care? Why should we improve stellar evolution models? And what I would like to highlight here in this lecture is, first of all, we have still unsolved and persistent problem in our understanding of stellar physics and stellar evolution. And what I would like to highlight in this talk, in this lecture, is how we can maybe solve this problem through multidimensional hydrodynamical simulations. And I want to show, first of all, how we can improve prescriptions in 1D stellar evolution models, and also how those numerical simulations could reveal some secrets that could not actually be grasped by current stellar evolution models. And maybe you are not working, on stellar physics or on hydrodynamical models, but I'm pretty sure that many of you are using stellar libraries to understand your stellar population, your galaxy, your extra galaxy. So you will be familiar with what I'm going to talk about. So first, I will focus here on one specific problem of fluid dynamics, which is what we call convective penetration. And here I'm in a very, very schematic scheme of what this process is. So what happens is when you have a convective zone and you have here a stable stratified zone, then we have the convective boundary defined by the Schwarzschild boundary, if you remember your stellar evolution lectures. And of course, the convective flows just do not stop at the boundary, but they penetrate through what we call convective plumes or penetrating flows. This is, I would say, well-known fluid dynamics problems that you can encounter not only in stars, but also in geophysics, for example, in the Earth atmosphere or in ocean. And it has been pointed, I would say, 60 years ago, the importance of this process in stars has been pointed, 16 years ago. So this is certainly a very focused fluid dynamic problem, but it's absolutely crucial in stars because it affects many, many stars. It will affect solar-type stars with a convective envelope, for example, and a radiative core. This will drive chemical mixing. This will transport angular momentum. It will affect any stars which have a convective core. So those are stars with masses greater than 1.2 solar mass stars. And this, process can affect the size of the core, of the convective core, the position in the Hertzsprung cell diagram, the age of the star. It can even affect the late stage of evolution of massive stars, even the supernova collapse, just before the supernova collapse. So why is it so important? It's just because convective radiative interface in stars is kind of ubiquitous. And it's ubiquitous during the life of most stars. And I illustrate this with well-known what we call Kippenhahn diagram, which shows as a function of time the structure here for a 25 solar mass star. And you can see that in blue, those are all the convective zones that develop from the beginning of the main sequence to very late stage of evolution prior to supernova collapse. And this process of overshooting penetration is happening everywhere where you have blue and white. So the big problem is that now, still nowadays, so 21st century, in July 2023, the treatment of this very complex fluid dynamical process is based on simple treatment, a phenomenological approach, where either we increase the size of the penetration region by a given fraction of the pressure scale height here, or we use a diffusion coefficient, which is also a fraction of the pressure scale height. So here we have three parameters that are usually calibrated through observations. And the problem as well is that you have many different options in many stellar evolution codes where you may change those three parameters depending on the phase of evolution that you are interested in. So you have really many options and you have a lot of degeneracy and a lot of freedom. So here I will just highlight the example of very broad impact that this process has, this physical process has on the evolution of stars. And there are also many observational evidences for the presence of this process in stars. So first of all, in terms of the broad impact, I think that people who are studying stellar population synthesis, so they know this problem of, and this uncertainty of stellar model using different free parameters to describe the efficiency of convective core overshooting. And this impacts the evolution of stars of different masses in color magnitude diagrams, for example, and the different colors just corresponds to models of the given mass, but with different efficiency of the overshooting parameter. And in terms of observational evidence, I will just show one evidence, which is, for example, the lithium depletion in stars. And we know also that if you do not account of overshooting in solar-type stars of low mass stars of different masses, then you are unable to explain the abundance of lithium which is observed in stars for different ages, like here in the Hyades at 600 million years. Models without overshooting cannot explain lithium. What I would like to highlight as well is that there is a very strong connection between, I would say, convection overshooting and between waves in stars, which connect stellar evolution with asteroseismology, and this is very important nowadays. And the reason for this strong connection is because convection itself and overshooting excite internal gravity waves and acoustic wave, then we can observe at the surface of stars, whether it's massive stars or solar-like stars. And those waves can provide crucial information on stellar structures, like the structure of the sun. It can provide information on the size of convective cores, and it can also provide information on the interior rotation rate of stars. So this is really very powerful. And just to give here some example, so we, from typically 3 solar mass star observations which are based on asteroseismology, we know that we need extra mixing to explain the asteroseismic data. And very recently, there were, with observation from TESS, there were evidence that we need overshooting to explain the mass of the core inferred by asteroseismology, and also it was possible to measure the rotation rate between the core and the envelope. So the problem and the reality is that when you analyze waves, you need stellar evolution models. And as I mentioned, the reality is that the treatment of overshooting, which is very important, is ad hoc, relying on 3 parameters. And now we know also that there are several issues with the treatment of transport of angular momentum in stars. And here, just to show an example, and I think this is really what those observations, they were observations of red giants based on what we call mixed mode, which clearly show the limitation of the transport of angular momentum in any state-of-the-art stellar evolution codes, which were unable to reproduce the measured ratio of the core to envelope rotation in red giant stars. So I think the main problem is that from waves, you need to compute stellar evolution models. You fit your waves and therefore infer mass of a core and rotation rates. But the problem is that waves have also an active role and can mix and transport angular momentum, which may then impact and feedback on the mass of the core you measure or you infer and the rotation rate you infer, and therefore it impacts on the treatment of those processes in 1D stellar evolution code. And this is a bit of the story of the snail biting its tail. And the problem is that now we really need more than ever very reliable stellar evolution models with the asteroseismology revolution, and with Plateau coming, this will be really amazing data and exquisite data. With the Gaia revolution, where we have million of stars to interpret, and we need reliable stellar models, without talking of the GWST revolution, where here I just quote the example of exoplanet detection, and when you see a planet, you see a star, and you need also reliable stellar evolution models in order to infer properties of your planets. So the best solution from my point of view is to develop multidimensional stellar hydrodynamic models in order to avoid the snail biting its own tail. But this is numerically extremely challenging. And the ideal simulation, which would actually cover the full sphere from the center to the surface of a star and over relevant stellar timescale, that is nuclear or thermal timescale, well, does not exist yet. So different groups have developed different strategies with the same motivation, that is to improve those phenomenological treatment in 1D stellar evolution code. And here, this is the second part of my talk, and because this is my privilege, so I will talk about the developments that we are performing within my own group and with my collaborators, and where we have developed a numerical tool, so it's numerical code, which is called MUSIC for multidimensional stellar implicit code. And those developments would have not been possible without the support of ERC grants. I think this is very important to mention, and also without the support of the supercomputer facilities, particularly in the UK. So, because we knew what we were looking for, we have some kind of design, this numerical code. I will not detail the specificities, but I think one important specificity is that it used realistic equation of state and opacities that are used also in 1D stellar evolution code, and rely on initial models from 1D codes. So this means that those 3D models or 2D models, those multi-D models, are very close to the 1D models that we want to improve. So here I want to give 2 examples. One example of the kind of, I would say, secrets or interesting phenomenon that those hydrodynamical simulations can reveal. And this example is based on work that we have done to simulate the convective envelope of solar-type stars. So typically a solar model. So when you do those numerical simulations, here you can characterize and you can analyze in depth the dynamics in the penetrating region. So you have here the convective region and you have here the stable region. And you can analyze, so this dynamics, what's going on there, and you can also analyze the thermal property of the flow penetrating in the stably stratified region. And what we have found, the simulations have revealed that is in this penetration region, there is a local heating which is due to the penetration of the plumes, and it's due to compression and to shear, which is induced by this plume penetrating in this region and heat up your penetration region. And you can see that by comparing the average temperature profile after many, many convective turnover timescale from the simulations with the initial profile, and you see that there is a bump in temperature in this region. And so this is here, this bump. And of course, what could be the impact of this local heating revealed by hydro simulations? And this is where, which is important, we always go back to the stellar evolution models and to the observations. So we can test that by implementing this heating in a 1D stellar evolution model of a sun and compare that to a model which is not modified. So this is what we have done. And if we look at one very interesting quantity, which is the square of the speed of sound, which is the ratio of pressure to density, and this is an important quantity for astroseismology, then we see that just in this penetration region, because of this local heating, we'd have also a bump of the speed of sound for the modified model compared to the non-modified model. Which is very interesting because this peak could explain or could help solving a well-known problem, which is the solar modeling problem. Yeah, we still have problems to model the sun, and helioseismology has revealed that because the solar profile inferred by helioseismology is showing actually a disagreement with standard solar models. So there is a problem, and we can see that here, this is the same quantity, the square of the speed of sound for a solar model inferred by helioseismology compared to a standard model, and we can see also this peak here as we see when we include this local heating. So this is very interesting. It's work ongoing, and this effect needs to be further investigated and may help solving the solar problem. So that's one example of the kind of secrets, I would say, that can be revealed inside stars thanks to those simulations. The other example I would like to show is how we can use those simulations to improve the treatment, for example, of overshooting, so kind of recipes that we're using in 1D codes. And here I will show the work that we have been doing, simulating the convective cores of a range of massive stars on the 0-age main sequence, so just at the beginning of the hydrogen burning phase. And here those are the models with the red dots. So those simulations can be analyzed, and for each stellar core and for each stellar mass, we can analyze in depth the, I would say, plume penetrating. So this is here the convective core, and you can see plumes going up and down, convective plumes, penetrating this stably stratified region. And for each stellar mass, we can infer an overshooting depth. From that, so here, overshooting distance, and we can therefore determine an effective overshooting width, where you will have extra mixing as a function of stellar mass. And this is what we show here. So I have as a function of the luminosity of the star, and here this is the overshooting depth as a fraction of the pressure scale height. And we can see here in blue this hydrodynamical scaling, compare to here a fit that can be made. What is interesting is that this fit, we find a scaling which is proportional to luminosity and to the size of the core, which is in line with the ballistic analytical model of Zahn developed in 1991, where he actually analyzed the deceleration of a penetrating plume by buoyancy force. And our hydrodynamical simulations confirm this ballistic approach. So now we can test this dynamical, I would say the hydrodynamical scaling, by implementing the scaling in 1D stellar evolution codes and comparing that to observations. A good test is the observed width of the main sequence where it can be determined empirically here in a Hirschsprung-Russell diagram, where you see the position, empirical positions of the 0H main sequence and of the terminal H main sequence. And this also is a well-known problem where models, without overshooting, this is here for models between 8 and 30 solar mass stars, cannot reproduce this observed width. When we implement the hydroscaling, so this calibration through hydrodynamical simulations, what is comforting is that we can explain, we can reproduce this observed width for masses below 10 solar mass stars. But there is still a problem going on for more massive stars above 10 solar mass stars. And this is ongoing, I would say, ongoing research. So typically we are underestimating by a factor of 2 the overshooting width. Possibly 3D could be an effect. Rotation may impact as well. We can also explore the effect of magnetic field. I'm not sure this will increase the size of the overshooting width by a factor of 2, which is what we need. But an interesting investigation, and this is further investigation, we are not the only one who are looking at that as well, is to look at the impact of a molecular weight gradient which developed above the core and which is due to the hydrogen burning during the evolution of the main sequence. So this is further investigations, and there waves may play a very important role in this region of the mean molecular wave. So talking of waves, those hydrodynamical simulations can be used also to characterize and quantify the waves that propagate, that are excited by convection and penetration, and that can propagate from the core of those massive stars up to the surface. So you take your, just for you to understand how we do that from numerical simulations, so you have your velocity field, you project that on a spherical harmonic basis. We describe, I would say, the geometry, the spatial properties of your waves. You take a Fourier transform, and therefore you can get a velocity for each of your waves for a given angular degree, azimuthal degree, and as a function of the frequency. And then you can get the power spectrum for the waves that are excited, and here I show for one specific wave as a function of frequency and as a function of the radius, where you can see waves excited, which in the convective core excited and propagating toward the surface. And what we can see here is that we can see a very strong attenuation of those waves toward the surface. And if we look at theory, just to understand a bit what's going on, you do linear stability analysis and you can predict the amplitude of waves with a complicated formula. But what is interesting is that here in this formulation, there is a damping factor, which, among other things, depends on the thermal diffusivity, which depends on the opacity of the stars and also on the density, and on the frequency. So low frequency waves will be preferentially damped. And the point is that thermal diffusivity in stars also increase from the center to the surface by typically 9 orders of magnitude. And therefore, to study waves in stars is very important also to have the realistic profile of opacities and thermal diffusivities. And the consequence of this is that those low frequency waves will be very strongly damped with 2 consequences. The first one, always with this motivation to try to connect those new simulations to observations, is that recently there has been observations of a low power excess in O and B stars from Corot and Tess. And this low frequency power excess has been interpreted as being due to those waves excited in the core and propagating to the surface. But from those numerical simulations, we think that is quite unlikely because of the strong damping of the waves, low frequency waves at the surface. And what is interesting also, and that the linear theory could not predict, is that the strong attenuation of waves at the surface can induce a heating of the layers toward the surface of your star, which certainly interesting consequences on the evolution and the structure of the star, and we are further investigating this. So you can see here, this is the temperature profile of the hydro simulations, which is coming from 2D simulations, and you can see in the outer layers that you have this heating due to wave damping compared to the 1D profile. So, coming to my conclusions, I would say that stellar hydrodynamic or multi-dimensional stellar hydrodynamic simulations are getting mature in order to be used to improve treatments that are used in 1D stellar evolution codes, 1D stellar evolution models, and which then rely, which are physically based calibration, and rather than ad hoc, which is always much, much better. And these numerical experiments, because simulations are numerical experiments, and they can reveal also some very interesting processes that could not be revealed by 1D stellar evolution calculations, such as the local heating in a solar model, or this wave heating in massive stars. But of course, well, the conclusion is the problem of convective plumes penetration and of transport of angular momentum still persist. But I don't think that we'll have to wait 60 more years to solve it. And the reason for that is that there are many groups as well, not so many groups to say the truth, not enough group, I think, from my point of view, but there are several efforts worldwide from different groups pushed by the same motivation to build what I call this 3 to 1D link and trying to improve stellar models with realistic star structures. And here I just want to show the hash-Poisson diagram of stellar hydro models where you can see the various efforts of the various groups, and you can see there are not so many stellar hydro groups worldwide, so various groups who are trying to populate this diagram with multidimensional models and try to better understand the complex physics in stars. And I thank you very much for your attention.
Thank you. Thank you very much for a very enlightening and very interesting talk. We have time for a couple of questions. There's one there.
Thank you very much. Could you comment on the stellar winds in massive stars and how, relative to the present models, how do they lose mass? This is very important, of course, for generating supernovae and black holes.
Okay, so first for the main sequence, mostly the winds for those stars is more important for the later phase rather than on the main sequence. So we've analyzed typically masses less than 20 solar mass star, and those hydro simulations are not, those are for stellar interiors. So you would need to have another approach, basically based on radiative hydrodynamics, to try to understand the stellar winds. So this is another uncertainty, absolutely, in stellar evolution. Another one, yeah. But this cannot be treated with this type of hydrodynamical simulations.
There's one question up in the back.
Thank you very much for a very interesting talk. I think this is very important work. And my question is on the helioseismology that you showed that you can mitigate this peak just below the base of the convection zone by this additional heating that you saw. But on the figure, it seemed as if that peak that you have from the simulation is about twice as high as the peak in the observations. So I was wondering if you could comment on that.
Yeah, absolutely. So I would say those simulations are 2D. And of course, we have to be a bit careful with 2D in the sense that it shows qualitatively, I would say, this process. We are now doing 3D simulations where this local heating persists, which is, of course, a very good thing, but the amplitude of the peak is smaller. So, which means that you always have to be also very careful with quantitative estimates, with numerical simulations. We highlight the process, and then we have to analyze the sensitivity. If we really want to measure amplitudes, we have to analyze the sensitivity of those numerical experiments with the resolutions, for example, with the dimensionality, etc., etc. So I'm not worried about that because I think it's robust against going to 3D, and we have also numerical simulations now with rotation, and it's also robust when you include also solar rotation, for example?
Thank you very much. I think in interest of time, we need to move on. And so let's thank Professor Baraf once again. Beautiful.
Thank you. Thank you again.
In 2023, we celebrate the 550th anniversary of the birth of the Nicolaus Copernicus, Mikołaj Kopernik, as we say in Polish. On this occasion, we will hear today the talk of Michał Kokowski, the professor in the Institute for the History of Science in the Polish Academy of Sciences. He is a physicist, he is a historian and philosopher of sciences. In 2010, he was awarded with the Nicolaus Copernicus Scientific Award of the Krakow City Foundation for his book titled Different Phases of Nicolaus Copernicus, Meetings with the History of Interpretations. And today, Professor Kokowski will talk about the perception of the Copernicus achievements in astronomy, physics, and cosmology.
Thank you very much. I'm very happy to be here. Thank you very much for the invitation to give a talk here. Okay. As professor said before, I work in the Institute for the History of Science of the Polish Academy of Sciences. It is the only one institute in a country which is interested in such subject as history of science. I also a chairman of a Commission of the History of Science, Polish Academy of Arts and Sciences, and editor-in-chief of Studia Historia Scientiarum, and corresponding member of International Academy of the History of Science and a member of European Society for History of Science. Okay, let's go. Okay, plan my talk. My talk is composed of 7 parts. In the first, I present some biographical data about Copernicus. Then I sketch 2 main strategies assumed by interpreters of Copernican thought. In the third section point, I will say something about various cognitive perspective or research hermeneutics assumed by scholars, interpreting Copernicus thought. And in the fourth section is about various scenarios. It is about the history of assessment of Copernicus' achievement and his originality. In the 5th point, I back to the present day, to the Nobel Prize in Physics 2020. In the 6th part, I will say something about methodology of exact sciences, and I focus my attention on the hypothetical deductive method of corresponding thinking. My last point is about Nicolaus Copernicus. I will talk about myths and originality, about scientific essence of Copernicus' thought, works, achievement, and scientific and cultural reception and importance of his thought. Okay. Some biographical data about Copernicus. Okay. He was born in 1473 and died in 1533. And he was inhabitant of Royal Prussia, subject of a Polish king, canon of Warmia chapter and scholastic of Wrocław chapter. That means he was a supervisor of the school of Wrocław chapter. He was a guardian of the altar in the Frombork Cathedral, guardian of the chapter table, administrator of chapter property, chancellor, deputy, envoy, lawyer, physician, economist, cartographer, and so on and so on. He had only minor orders. He was not a priest. As a hobby, he dealt with translation from Greek into Latin, and in 1509 in Krakow, he published book Theophilacti Scholasticissimo Cati Epistole Morales, Rurales et Amatatorie, Interpretatione Latina. Therefore, he is a flagship figure of Polish classical philology. It was the first translation from Greek to Latin in Poland. And also, as a hobby, Copernicus dealt with all his adult life with mathematical and physical astronomy and cosmology. And it is the reason of his lecture. Okay. Two main strategies. We may assume very simplified approach. We may read textbook, and in such textbooks we haven't place to consider detailed matters. And the second approach is very detailed studies, when we find many possible sources and critically trying to understand its essence, and so on and so on. Okay, let's go to the third section. Various cognitive perspective or research hermeneutics, the means used to interpret information. People who are interested in Copernicus' thought may assume different strategies, cognitive perspectives. I mention only four. General history of exact science, history of medieval philosophy, history of medieval astronomy, and history and philosophy of science. Let's go to fourth section, various scenarios. I will say something about the history of assessment of Copernicus' achievement and his originality. And from a perspective of general history of exact sciences, we look for statements of various scholars from the times of Copernicus and after Copernicus, the Wittenberg Astronomical School, Tycho Brahe, Riccioli, Kepler, Galileo, Newton, and so on, Einstein, Poincaré, and so on, and so on. Okay. From the perspective of history of ancient philosophy, we see that Copernicus was a continuator of a Pythagorean thought. Philolaus, Niketas, Heraclides Ponticus, and Quantus, Aristarchus of Samos, and so on and so on. Okay. From the perspective of history of medieval philosophy, Copernicus was a continuator of late scholastic thought, Buridan, Orem, Albert of Saxony. Okay. From the perspective of history of medieval astronomy, Copernicus was almost an idolater of ancient science. Or he was the last student of Maraga's School of Astronomy. Or, according to other group of scholars, he was a continuator of Proclus. Okay. And now, from the perspective of history and philosophy of science stands first. Copernicus had no new kind of observations. He rejected God-centrism on philosophical grounds, Pythagorean, Platonic views. Okay. From a perspective of history and philosophy of science stands too, presented by Thomas Samuel Kuhn and Paul Feyerabend, there is no scientific method, and the subsequent theories are incommensurable. Copernicus revived the ancient hallucinogenic ideas, according to Kuhn. He did not prove motion of the Earth, and the predictions of his theory were no more accurate than those of Ptolemy's theory. It was the idea of Kuhn and Feyerabend. And there was Copernican revolution, according to Kuhn. According to that stance, from the perspective of history and philosophy of science, assumed by Whewell, Popper, Lakatos, Zachar, Hanson, and me, Copernicus, Ptolemy's, and Brahe's theories are not equivalent formally and observationally. It was the idea mentioned firstly by Hanson. There is a scientific method. According to Whewell, it is the sophisticated induction. According to Popper, the hypothesis method. According to Lakatos and Zachar, the method of the research program. And the hypothetical-deductive method corresponding thinking, according to me. Let's go to back to the present day, the Nobel Prize in Physics 2020. The Nobel Prize was divided one half to Roger Penrose for the discovery that black hole formation is Weber's production of the general theory of relativity, and the other half jointly to Reinhard, Genzel, and Andrea Ghez for the discovery of supermassive compact object in the center of our galaxy. In the very interesting lecture given by Professor Reinhard Genzel Nobel lecture entitled 40th Journey Nobel Prize in Physics 2020, we find very interesting figures with very important graphs. Okay. The three are most important for me. It is the graph about stellar orbits and general relativity effects, gravitational redshift and Schwarzschild precession. They are important because they are strictly linked with the methodology of exact sciences and the method, hypothetical deductive method of corresponding thinking. I explain this in this section. In contrast to philosophers of science and sociologists of scientific knowledge of the last 70 years, I think that there is a scientific method of exact sciences. I call it the hypothetical deductive method of correspondence thinking. The method is composed of complementary parts: the hypothetical deductive method and the method of correspondence thinking, gamma of thought experiments with constants of nature, and the eraser method. The eraser method I explain later. Okay, using this method leads to the construction of mathematical physical models of natural phenomena and the discovery of scientific laws that are not just social agreements. The key role in the method of correspondence thinking is played by a postulate of correspondence of successive theories and its realization, a correspondence principle of successive theories. The correspondence postulate of successive theories states that the more general new theory should be linked with the old theory by a corresponding principle, and, it is important, this does not mean necessarily apply to all physical quantities. Okay. The corresponding principle of subsequent theories states that the more general new theory reproduces, imitates the properties of the old theory in some limit boundary region, and this does not necessarily apply to all physical quantities. Standard example, we see normal mice defined in special relativity theory, and in classical mechanics mass is constant. In special relativity theory it depends from velocity. Okay. One remark, George Gamow, thought experiments. It is a very important strategy assumed by any theoretist. When we change these values, we much better may understand what we have a model, what our theory is. And okay, Mr. Topkins, Gamow wrote fantastic, popular, but it's a book, but really it's very, very good book, which I think should know all the representative exact sciences. Okay. In contrast to Popper, Kuhn, and Feyerabend, I think that there are scientific revolutions consisted of some evolutionary and some revolutionary changes. Exempli gratia, new mathematical language, new hypothetical quasi-entities. And scientific revolution happen when new class of phenomena are modeled and new observables are established, and when the new theories are related to the old theories by certain correspondent principles. Okay, let's go to the last point of my section, or of my talk. Back to Nicolaus Copernicus, myths and originality, scientific and cultural reception and importance. Okay, well, let's start from myths about Copernicus and his originality. I list 8 such myths. First, Copernicus was almost an idolater of ancient science. Second, Copernicus was not an original astronomer because he brought back to life the system of Aristarchus of Samos. Third, Copernicus was not an original astronomer because he brought back to life the ideas of motions of the earth considered by Buridanist, the late medieval scholastics Buridan or Albert of Saxony. 4, Copernicus was not an original astronomer because he brought back to life the Pythagorean ideas of motion of the Earth, according to Kuhn. And 5, Copernicus was not an original astronomer because he brought back to life the mathematical ideas considered by medieval Arabic astronomers, the removing of which considered the removing of equants and the so-called 2C device. Okay. 6th, Copernicus' system was not better than Ptolemy. 1, because these systems were equivalent formally and observationally. 7th, Copernicus' system was not better than Ptolemy. 1, because the Copernican frame of reference and the Ptolemaic frame of reference are equally valid from the perspective of general relativity. And 8th, Copernicus was the author of Copernican principle. According to Hermann Bondi, it states that the Earth is not a central specially favored position. In fact, Giordano Bruno was the author of this principle. What is the essence, scientific essence of Copernicus' works? Copernicus formulated 2 astronomical theories, simplifies, special, and general, describing 2 works, the Hypothesibus motum celestium constitutuis commentariolus, circa 1503, and the Devotionibus orbium celestium, published in 1543. Copernicus' theories describe the position of fixed stars and planets for each time. He used plane and spherical geometry for this purpose and created a combination of cycles and spheres according to the axioms of Hellenic and Hellenistic astronomy. Copernicus' theories are not heliocentric, but heliostatic. The center is not the physical sun, but an abstract point called the middle sun, the center of the Earth orbit around the sun. It is a very important issue. Then, Copernicus' main astronomical cosmological achievement was to find a new harmony of the universe. He introduced an ambiguous arrangement of celestial bodies and rejected the principle of ordering the system of Ptolemy assumed by him in Almagest and planetary hypotheses. There was the Copernican revolution in science. You see brackets, it's in the letter R. It's very important. It's completely different than Kuhn's idea of scientific revolution. And Copernicus' main methodological achievement was to formulate 2 theories, general Copernican theory and special Copernican theory, which are linked by certain corresponding principles. These theories are also linked with Ptolemy's theory by certain corresponding principle. And, example, from Commentariolus, on the first figure show the model of first anomaly, according to Ptolemy in Almagest, and second, the model of first anomaly in Copernicus Commentariolus. We see that these functions differ. However, they are perfectly agreed observationally. On the first figure, we see a tangent of the equation center and tangent of the difference of the equation of center. These differences are very, very small. These 2 functions agree really beautifully. Okay. The Devotionibus, Copernicus assumed an analogous approach, and for instance, he used it the constructing function of precession. In Copernicus' theory, according to Copernicus, this function is a combination of linear function and sinusoidal one. According to Ptolemy, it's only a linear function. And also, we see these graphs and the difference, limit region. Okay. Similar approach, I assume, analyzing equator inclination. Okay. And what was the scientific reception of Copernicus' achievements? The achievements of Copernicus contributed to a decisive revival of development of astronomy and physics from the 16th century to the 21st century. I will not... okay, briefly. Wittenberg School of Astronomy in this school, scholars, members of this school, inverted Copernicus system to geocentric system. Then Tycho Brahe inverted Copernicus system to the Tychonic system and made very important correction of parameters of Copernicus theory. He used the Rayleigh method. He dilated some Copernicus long period phenomena. And then we have Kepler, Galileo, Isaac Newton, D'Alembert, Euler, and so on and so on. And finally, Albert Einstein. Okay. And very important question. Why was Copernicus an important thinker and still is? The answer for this question is given by cultural cosmology. And I explain this matter. General cultural humanistic cosmology is a combination of the basic ideas of scientific cosmology and religious views in force in a given time, epoch. Cultural cosmology creates a mental stage relating to on which our lives take place here and now in society. It's very important. We live in symbolic world. We not only eat, we also every time lived in symbolic, very complicated worlds. And in Christian culture, geocentric cosmology was the health-centric, the least worthy place was the center, and the most worthy, the periphery, the heavens, the seat of God. The theories of Copernicus destroyed the geocentric cosmology, which had been integrated for 2,000 years with the rest of culture, religion, art, and so on and so on. And triggered the development of human philosophy, Christian theology, and new cosmology, which from the times of Galileo, Kepler, and Newton was heliocentric cosmology. General relativity theory overthrew the 18th, 19th century belief in the truth of the heliocentric system. Nevertheless, it was still an important cosmological achievement because it led to the construction of Newtonian physics and then general relativity. Conclusion. Copernicus, however, was an original mathematician astronomer. Firstly, he creatively continued the philosophical and scientific discourse on astronomy, initiated in Hellenic and Hellenistic culture, cultivated in the medieval Arabian culture and the medieval and Renaissance Latin culture. Secondly, he empirically restored renewed astronomy, therefore he was called the second Ptolemy. Thirdly, he consciously used the means of the hypothetical method for corresponding thinking. We must emphasize, it is impossible to achieve the result of Copernicus by chance. And fourth, Copernicus influenced the further development of physics, astronomy, and scientific and general humanistic cosmology from the 16th century to the 21st century. And bibliography, and thank you very much for your attention and invite you to discussion.
Thank you. We have time for questions. This one.
Well, thank you so much for your very interesting presentation. So the question is, was this vision of the heliocentric world first proposed by Copernicus ever, or were there any other cultures, perhaps not Western cultures, where the heliocentric vision was the basis of cosmology or cosmogony?
Oh, it's completely different worlds. For instance, as I said, medieval world was very ordered. It was a fantastic world. It was finite. It has only 20,000 of radius of the Earth, and this vision was integrated with all parts of culture. When Copernicus formulated new theories, he of course mentioned previous scholars who thought about different systems, heliocentric system, Pythagorean, Platonic, and presented a very complicated theory. And this complicated theory, Copernican theory, influenced further development of physics, astronomy, and cosmology, also humanistic cosmology. When the Earth is in the middle of the universe, we have completely different philosophical view about style of thinking, about the world, about life, and so on and so on. But in 17th, 18th, 19th century, many philosophers, sociologists, introduced new ideas, and it was a problem was also linked with psychology. The world after Copernicus, in the Deuteronomy, Copernicus said that the universe is similar to infinity, but Giordano Bruno stated that the universe is infinity dimension, has the infinity dimension. So it is a completely different place, because in Giordano Bruno, for instance, we have a universe composed of many solar systems. Where lived also intelligent beings. So it was then strictly connected with theology, Christian theology. If there are different universe, different solar system, then where is this one the most important? Where God was born, and so on, and so on, and so on.
Thank you so much.
Okay. Do we have more questions? Oh, there's one here.
Okay.
I was not fully aware that this argument related to hell was so important to put really the Earth into the center of the universe. Because of course localizing hell inside Earth is kind of natural. We know volcanoes since thousands of years, so of course that had to be inside. But I was not aware that this was additional motivation to keep the Earth also as a center of the universe.
Yes. Heliocentric, hell-centric idea was, of course, product of Christian culture. Before Christian culture, we haven't such idea. Nevertheless, after when the Earth was not in the center of the universe, it was changed the structure of the universe. That means this hell was through for heavens. So some problems, complicated problems, were created for philosophers of science, for philosophers. So, of course, differentiate between humanistic cosmology and scientific cosmology. For Copernicus, a heliocentric idea was he didn't use this idea in his theory at all. It's a different dimension of culture.
Thank you, Professor. Let's thank Professor again. And we move to the last talk.
Okay, so now we have our next plenary speaker, Professor Jose Cernicharo from SIC in Madrid. Professor Cernicharo, as many of you will know, is one of the leading figures of astrochemistry over many years now. He has a broad bibliographic history from spanning very often in infrared, which is also what we will hear about today, from ISO through to the present day with ALMA and JWST. He's also a very highly regarded scientist. He's also, during his career, also been, among other things, a leader of an ERC Synergy grant in Madrid, and reunions observations and laboratory work to understand what's going on in the molecular part of the galaxy. So please, Professor Cernicharo, it's a pleasure to have you here, and the stage is yours.
Okay, thank you very much. I would like to thank the organizers for inviting me to talk about molecules in space. And what I am going to do is to explain how we detect molecules and what are the techniques and the methods that we use to that. And I would like to say that 50 years ago, practically nothing was known about the physical properties of interstellar clouds. We knew that they contain dust grains, but no idea about what the gas composition was. And this is something that has been solved by radioastronomical observation, but also observations in the infrared using different space platforms. And here you have a comparison of the same region, the Taurus complex or dark clouds, at the left, and in the right you have the CO emission. You have a very, very good correlation between the dust grains and the gas in the clouds. This is something that has been done during the last 50 years using different radio telescopes and detecting a lot of new molecules. Then my talk will be devoted to astrochemistry, but particularly to the detection techniques, and I will talk about molecules as tracer of the physical conditions, and mainly about line surveys, because line surveys is the way we detect the complete census of molecules in dark clouds. And at the end, I would like to talk about line surveys, but of a cold dark cloud, just in Taurus, that have provided a clear revolution in our way we think about some special molecules. 70 years ago, Charlie Towns proposed that some molecules should be present in space. And in particular, he was talking about carbon monoxide, hydrogen cyanide, carbon sulfide, many, many species. He provided a list of frequencies that were coming from laboratories doing molecules, but unfortunately at this time, no receivers were available to do observation at these frequencies. And at the time of Charlie Towns' suggestion, only 3 molecules were known to be present in space, CN, CH, and CH+, that were detected in the optical spectra of diffuse gas in the direction of a slightly reddened star. In the 10 years after the Charlie Towns proposal, ammonia was detected, water was detected, and also formaldehyde. in the centimeter wave domain using the Hack Creek telescope and the Green Bank 145th telescope. And then something happens in 1970. Wilson, Jeffers, and Penzias, the same Penzias and Wilson that provide the cosmic background radiation detection, they detected carbon monoxide in the direction of Orion. And it was a surprise because whatever they point the telescope, they found the line. Carbon monoxide was an ubiquitous molecule in our galaxy, and as we know now, it's a molecule that can be found in external galaxies too. During 10 years, more or less, the Keep telescope detected something like 30, 40 molecules, and at the beginning of the 80s, something like 50 molecules were known in space. Then 3 new instruments become available for the community, the Iron 30-meter telescope, the Noveyama 45-meter telescope, and also the Green Band telescopes. Then between 1980 and 2020, something like 200 molecules were detected in space. However, since 2020 and right now, there are something like 300. It's a factor 1.5 in 3 years due to the revolution that has been provided by 2 line surveys, one with Green Band, another one with the Jebes 40-meter telescope, Gotham and Kirchhoff. This is the list, and it's every time more difficult to put all the molecules that have been detected in space in one transparency, but here you have all the molecules that have been detected, and you see the number for diatomic, triatomic, 4 atoms, 5, 6, and it seems that the number of molecules decrease with the size. This is something that 3 years ago, it will be even worse, because the number of molecules that have been detected in the last 3 years belong to the polyatomic molecule with more than 6, 7 atoms. And this is something that limits the search for chemical complexity. What is the limit? Limit is sensitivity. If you want to detect big molecules, you need to know that the partition function, the rotational partition function will increase as the number of molecules, of atoms in the molecule, and then the intensity of the lines will decrease. Then detecting more and more complex molecules requires sensitivity. Here you have a plot of the contribution of the different telescopes to the number of molecules in space, and then you can see that there is a telescope that is providing the largest number so far. Around 2021, it was the 30-meter Iron telescope. And the molecules, in addition to the peculiarity that they are complex and that they are in space, they are used by radio astronomers to derive the physical conditions of the interstellar and circumstellar clouds. When you have the possibility to observe several rotational transitions of a molecule, you can derive the volume density, the temperature of the gas, and the abundance of the molecule. We need also, we need to take into account that radio astronomy provides very high spectral resolution. We have resolutions in kilometers per second, fraction of kilometers per second, that allows to study the kinematics and the dynamics of the clouds. And more recently, we have also the possibility to observe with very high angular resolution thanks to the BLA, to ALMA, to NOEMA, and to other interferometers. In the infrared, we can study light species not through rotational lines, but through vibrational transition, and only for very light species like water, OH, CH, you can also detect some rotational transitions in the mid and far infrared. As an example, we have a very recent detection of one of these light species, CH3+, by Vernet et al. With the James Webb toward protoplanetary disk in Orion. While line surveys is the way we search for the chemical complexity, we need sensitivity, and what is important to understand is that what is done today in 24 hours could require several years of observing time in the 70s. This is because we have improved a lot the sensitivity of the receiver, the bandwidth of the receiver, and the spectrometers behind them. You have here a list of some sensitive line surveys. Practically all the prominent sources, the most prominent sources in our galaxy have been studied at different wavelengths. from the centimeter to the millimeter, 2 millimeter, and far infrared. I am going to show some examples before going to the line surveys in the centimeter domain by Gotham and the Quixote. And here you have an example of what is the problem when you are doing a line survey. This is this observation correspond to Orion. They were done by Tercero et al., 3, 2, and 1 millimeter. Here you have the rotation, the emission of the molecules between 200 and 280 gigahertz. You see all this kind of line. It's a forest, a real forest of lines. When you make a zoom in frequency, you see that there are some lines that are broad, others that are narrow. This is because in the beam of the single disk that was used for these observations, you have many sources. You have several sources with different physical conditions, and then they produce some confusion. And the confusion is at this level when really you don't know where is the baseline. Everything is real. They are lines. These observations are taken in a few minutes of observing time. This is something that is a limit for the study of complexity. How to solve this problem? Well, if we can resolve the different sources, that means going to interferometers, then you can study the contribution of the different sources. Here you have molecules. Each box corresponds more or less to the size of the 30-meter beam, but now with an angular resolution of 1 second. And here you have contours that correspond to one transition and color that correspond to a different transition. And then in different points, you can see how the abundances of the molecule change. This is due to the fact that during the collapse of the cloud, the molecules stick into the dust grains. They produce ices. In these ices, you have very interesting chemical processes, and they are waiting that something hit the grain, for example, a new star or a shock. And then all the molecules that have been produced on the ices of the surface are released to the gas phase and make a very complex chemistry. And this is something that has been really studied in detail by several groups, but in particular by Garrett and Herbst. And when you have the possibility, this is another example, when you can separate with your telescope the different sources, you win a lot concerning the study of the physical properties. Here you have an example of classical source that has been observed by Jorgensen et al. With ALMA, and then the source is separated. There are two sources separated by a few seconds. Here you have the spectrum toward one of them, the A, and here toward the B. You see that they are different, very different, because the chemical composition is different due to the different chemical effects that are occurring at the different objects. Here you have the same object, but with a 30-meter beam. That means everything together. And then you see that you reproduce the line, but you don't have information about the chemistry. This is something that is important to take into account. And I would like to say that in addition to interstellar clouds, circumstellar clouds, evolved stars, red giants, have played also an important role in the evolution of astrochemistry. Practically a few years ago, practically 50% of the molecules detected in space were discovered in one object, one carbon-rich star, IRC 10-16. Now, with the new molecule detected in interstellar clouds, practically 30% of the molecules known in space have been detected in this object, and in particular, there's something peculiar to this kind of object, is the presence of metals. You have all these metals that have been detected in just this object, IRC 10-16, with magnesium. And in particular, this discovery of cations of magnesium with carbon chains that are produced in the external layers of the circumstellar envelope. Also, these objects can be studied with very high angular resolution, like in the case of ALMA. Here you have a plot of some ALMA observation of IRC 10-16 in black. And you see a lot of U lines that we don't know what they are. They are probably the carriers of these lines are the molecular sheets or dust grains. Dust grains are formed around the photosphere of these objects, and all these U lines, we don't know what they are, we don't know what kind of molecules, probably metals, but we don't know yet. We need some information. And here you have an example of observations of this object IRC 10-16 from the inner part. This is the contours correspond to the continuum, and the colors to SIS and HCN at the scale of 0.1 arc-second. Angular resolution was 20 milliarc-seconds. Here angular resolution is 0.6 arc-second. Here angular resolution is 2 seconds. Here is 10 seconds. There is a factor 1,000 between this picture, and this corresponds to all the chemical variation of the physical properties between the external layers of the circumstellar envelopes, where temperature is around 20 Kelvin and density is 10 to the 4 particles, to the inner part, which temperature is around 1,500 Kelvin and density is 10 to the 10 particles per cubic centimeter. You have very different chemistries between the internal and the external parts, and astrochemistry is providing you with the way to study the chemical processes from the photosphere with dust formation to the external layer where the gas is injected into the interstellar medium. Then we can do also infrared line surveys. This is something that was possible thanks to Texas and XS on SOFIA, because they provide very high spectral resolution in the mid-infrared domain. And here you have an example of what you could expect, what you observe in the infrared with Texas toward IRC 10-16. Every feature here is real. You see lines of acetylene, HCN, SIS, and isotope log of sin absorption. The angular resolution is 1 arc-second, but thanks to the PCE profile, it is possible to model with a very high angular resolution the abundances of these molecules in around the photosphere of IRC 10-16. Then, just to summarize a bit what we do in astrochemistry, this is a multidisciplinary field. We observe molecules using radio telescope or infrared telescopes, but we need the help of chemical physics, because in order to interpret our data and to do radiative transfer models and chemical models, we need collisional rates, state-to-state collisional rate between our molecules and H2, helium, and atomic hydrogen. We need a very good or high accuracy determination of the frequencies of our molecules, and we need reaction rates. And this is something that is done in the laboratories, and during the last 50 years, we had to thank our colleagues that had developed very complex instrumental setups to measure, to derive for us this parameter corresponding molecules. They had done low temperature measurements of reaction rates, rotational and infrared spectroscopy, studies of ICES, state-to-state collisional rate, and so on. Then chemical complicity in cold dark clouds. This is something different. Temperature is now 10 Kelvin. It's no Orion. In Orion, the temperature is 200 Kelvin. In IRC 10-16, temperature varies between 1,500 and 20 Kelvin. Here, the temperature is 10 Kelvin. What we can expect? And GOTAN is a line survey of TNC1 done with the 100-meter green band telescope between 1 and 50 gigahertz. They don't have sensitivity enough to detect individual lines, but they have a very powerful techniques of statistical stacking of the data to produce detection, and they have discovered several cyanide derivatives of benzene and naphthalene. And you have here the reference for Maguire et al. And the question now, okay, we have these molecules. How these molecules and where in the cloud are formed, these pHs? And to give an answer to that, we build receivers within a synergy project of the ERC that was called Nanocosmos. And the project, we call it Quixote. Quixote is, as you know, was always fighting against something. In our case, we were fighting against noise. Our idea was to have a very sensitive line survey, to go to see things that no other radio astronomers have seen before, because we want to reach the sub-millikelvin level. This is something that has never been done. And we would like to detect molecules by a classic techniques of detecting all the lines of the molecule. The 40-meter telescope that was used for this observation is in Spain. at more or less 900 meters of altitude, at 60 kilometers away from Madrid. Probably you don't know it. It's called EAS Observatory. It's a very good telescope for observation in the 30 to 50 gigahertz domain. And here you have the Quixote survey of TNC1, the same source that forgotten, and it is true. There are only a few lines above 400 millikelvin. However, when you make a zoom, you see that the number of lines, this is 5 millikelvin, and this is the noise of Quixote by February 2023. We can make a zoom to see what we have there. You see a forest of lines. There is thousands of lines. Many of them are from unknown species, others are from isotopologues of very well-known species, and this is an ongoing line survey. And the final goal is to reach a sensitivity, a 5 sigma sensitivity of 0.3 millikelvin, something that will be reached within a couple of years. But waiting for that, the first thing, when you have something that is new, because the instrument was completely new, and we were wishing to detect things at very low level. Then you have things like that, and you can say, there's a big noise, or this is an instrumental problem. However, when you look to the line, they are at the 2 millikelvin level. The center of the two lines are in the ratio 1:25, 5:4. This is the typical behavior of the two rotational transitions. And we provide the data with the expectation we have for the rotational constant of the molecule. We provide the laboratory with information about that, and then we get something like that. The data are real. You are seeing a radical H2C3N, and that is a proof of the quality of the data that we can reach by integrating using new instrumentation. TNC1 can be used as a spectroscopy laboratory. Many molecules have been detected without any information about the frequencies, just using TNC1 like a laboratory for spectroscopy, looking for special patterns in the frequency, harmonic relation, and other typical pattern of molecule that could be translated into rotational constants, composition, if it was a radical, if the molecule contains nitrogen or hydrogen, producing hyperfine structure. Then we had detected all these species without any information. And one thing that is really the most important aspect of this kind of observation is to look for the intermediates, the molecules that are playing in the chemistry a role in the formation of bigger and bigger molecules. And Quixote has the possibility to detect molecules with very low dipole moment. That means hydrocarbons. Pure hydrocarbons have very low dipole moments, but we have detected many of them. You can see how complex they can be, and some of them extremely abundant as, for example, HC3N or very well-known molecules in TNC1. And then we can detect molecules as complex as those that you have on the screen. Indene, cyclopentadiene, this is an aromatic molecule, this is a pH. And the technique for detection of indene is you see the lines, 1, 2, 3, 4, 5, 6, 7, all the lines are there. This is a robust detection of the first pH in a cold dark cloud. The same thing for cyclopentadiene and benzene, that is also a very complex molecule that's very well known on the Earth. It's playing a key role in combustion chemistry, but it's also present in this dark cloud and probably producing playing a role of intermediate for bigger molecules. Derivatives of cyclopentadiene, fulvenanen, and here I would like to say something that is important. There is just a few reactions. When you add a few reactions to the chemical network, in this case it's C3H3 plus ethylene, you change completely the results. But the problem is bigger than that. It's not just one reaction, because when you look for all the molecules that have been detected toward TNC1, and you consider the most abundant one, all the data are coming from the Quixote line survey, the pink dots correspond to chemical model because these molecules don't have permanent dipole moment. And you see that in this region, just with a few reactions, you could produce bigger and bigger molecules, but nothing is known. A lot of missing reactions have to be introduced in our chemical networks. And this is something that, again, we will need for that the collaboration of laboratories doing whether experiments or theoretical calculations. And one of them, of these cations, has been recently detected with Quichotte, and using laboratory information from Cologne, we had detected the C3H3+ molecule. Here you see the lines, the laboratory information, and this kind of detection will permit us to go further in our chemical models. And the summary, well, more than 46 molecules in TNC1, many other molecules in IRC 10-16, in particular magnesium-bearing species, and in other sources. And none of these molecules have been detected in the carbon-rich star IRC 10-16. During many years, pH hypothesis was that pHs were formed in carbon-rich star. No, there are no pHs in carbon-rich star. All these molecules are not detected there. pHs are detected in protoplanetary and planetary nebula and in the photodominate regions. But in the carbon-rich star phase, there is no pHs. And then here you have a plot again, the same plot, showing Jeves and the number of molecules detected now by the Jeves telescope. It's a Spanish telescope, I am proud of that. Is similar to that of the 30-meter iron radio telescope. And now the question is where these pHs are formed. And in order to give an answer to that, we need information about the spatial distribution of these molecules. And this is complex because the lines are weak. But there is Sancho. Sancho is the fidel companion of Quichotte. Sancho is a full map 4 minutes by 4 minutes with a sensitivity of 2 millikelvin per pixel, and thanks to that we can derive the spatial distribution of benzonitrile that is a proxy for benzene and for pHs in TNC1. And this spatial distribution, when you compare with other molecules, now the contours correspond to benzonitrile and the colors to different molecular species. Here you have methyl acetylene, C3H2, you see that the distribution is the same. This is a bottom-up process. We need to understand what reactions are producing benzene, naphthalene, and indene. But now we have the information. And just to say that in the future, Quichotte will provide, I think, like 40, 50 more molecules, because we expect to have 2,500 U-lines in this cold dark cloud before we reach confusion limit. That probably will happen at some moments. And we will have very nice, very sensitive map, 2D maps of the region. Then, in the next year, we could understand more about the chemistry of pHs and the chemical complexity in space. Thank you very much.
Thank you very much. I think we missed the trick by not having a quiz after this in the break. Questions?
You mentioned that those U lines are signatures of dust grain formation. And the temperature of this of the medium you study is quite low. On the other hand, I think we have dust formation in HGB stars or something like that with much higher temperature. So would you say that you can form dust in semi-any temperature, or this low temperature is actually favored?
Well, let me go back to the picture of IRC 10-16. Here. The temperature there is around 1,500 Kelvin, and this is the region in which dust is formed. As soon as the temperature goes down to 1,000 Kelvin, everything is molecular, And in particular, you have metal-bearing species that are very refractory, and they will make the seeds of dust grains, or the molecular seeds. The temperature when you go to this region, for example, is 1000 Kelvin, and when you go outside, it's 20 Kelvin. Then everything concerning dust formation is produced in the region between 5 and 10 stellar radii, where the temperature is between 1000 and 1500, 2000 Kelvin.
Okay, thank you.
So there's one more question up in the back. It's very hard.
Thank you for the fantastic talk. It might be a very simple question, but it's still a question. All right, so you showed a lot of molecules, and in all of them, the number of hydrogen atoms is comparable to number of other more heavy elements like carbon or nitrogen, or for example, silicon. And my question is, like, you know, there's much more hydrogen atoms overall in the ISM than other atoms, and is there a very simple reason for that difference, so that it's much more in atomic form of hydrogen, but much fewer in molecular compounds?
Well, the number of hydrogen atoms in the molecule depends a lot on the temperature and the chemical conditions of the cloud. In some clouds, you have saturated species with a lot of hydrogen in the molecules. In other sources, you have radicals. We use one hydrogen or two hydrogen in the molecule. This is the case of the dark cloud TNC1. This is because H2 doesn't react very often with the molecules. I mean, you need some special conditions in order to have reaction of H2. H2 react very well with H2 plus, for example, to produce H3 plus, but H2 doesn't react, a low temperature doesn't react with radical like CCH or C4H. You need temperature to produce the reactivity of H2. Then depending on the physical condition, you will have a different degree of saturation, or hydrogen saturation in the molecules.
Thank you.
Okay, in order to not... Oh yeah, so let's take a last question here, and then I think we have to move on not to cause delays in the program.
Yeah, I'll make it quick. Then, thank you, Jose. Very nice lecture. Remind me of organic chemistry lecture when I was doing studies. I was just curious, can you tell me what's your opinion? Because many of the observations have been done basically in the sub-millimeter and millimeter. But as you know, SKO is there in the future. Different frequencies, especially band 6, for example, could be of interest. What do you think in terms of the studies of these molecules could be done there?
Well, the frequency domain has to be selected in function of the size of the molecule do you want to study. If the molecules are big, the rotational constants of the molecule will be low, and then the frequencies of the peak emission will be produced at lower and lower frequencies. For example, molecule like C4H or C5H or C6H have the emission peak in an object like TNC1 in the Q band between 30 and 50 gigahertz. If you have bigger molecule like the PHs, the emission peak goes down. And then which is the best frequency domain depends a lot on the molecule that you want to observe and the chemistry that you want to address. Millimeter and submillimeter during many years have produced a lot of discoveries of molecules with 3, 4, 5 atoms. Going to higher sizes, you need to start to go down in frequency. This is why Goten and Quixote have provided a lot of new discoveries by focusing on the Q band, mainly in the Q band and also in the K and Q bands. And if you want to study the physical condition, maybe you have to address the study of hydrogen cyanide at different rotational transitions, and then you have to go to the submillimeter domain, or carbon monoxide, or any other molecule with many rotational lines. If you want to study chemistry and to see the chemical complexity of the clouds, well, maybe you have to search at all the frequency domains if possible. But depending on the size, you will have to make a choice, the size of the molecule.
Okay, thank you very much. I think let's thank Professor Cernicharo and all the speakers. And enjoy your shortened break.